So, but I want to do a different demo that involves basically everything up till now. And I'll try tessellation shaders maybe next week. Cool. So project 1 now. What I want to do is actually show a few ways to solve the find best. That was the one I got most questions with, and that one has a lot of ways to answer it. And I think a lot of people added stars and brackets and ampersands and things until it worked. And then they were like, hey, it works now. No problem with that. It's a good way to go. Okay. I think I might have P1 on here already. Good idea. Okay. So there's the solution file. And so I suspect most people made some kind of bundle and then assign these to things. So you can make something up here. I think find best returned to end, if I remember right. And I have to say void star up here, unfortunately. This is the function list, and then we got a parameter and then a size key, which is like the list. Okay. So then that goes into a bundle like this. Doesn't have to be called the same thing, but it is here. Okay. And then it's going to actually need 2 other function pointers there before everything works right. Okay, so something like that. Okay, so the real trick up here is iterating through FL because you want to go through each thing in it. So you have something like ni equals 0, I is less than len, I plus plus, and then you have like kind of a CS108 kind of find maximum argument. In max index. I typed it in. So you have both these kind of like that. And max could start at 0, for example, and that's fine. As long as they're all negative. If they were all negative, that wouldn't be okay. Okay, so you got something like that, and you want to return the max IDX again. Okay. And so then you just have to know if it's bigger than the current max. FL at position I dot, I don't know, we have to call it, is greater than max IDX. And so if that's the case, then we just have to update. Okay, equals. So whatever came back from it. So it might be easier to save it. Okay, now. Okay, so I suspect most people have something kind of like that, except that that line doesn't actually work. Let's get the rest of this thing together here. I'm not going to make it work right. So the sorted copy one returns an int star. I'll call it SC for sorted copy. It takes a int star and a len. Okay. And so since I don't actually want to write this one, I'll just say return list. That should keep it happy. And then we got the compare one, which takes 2 ints. Okay, we'll just return A. So it'll say that these aren't any good. Okay. So I think that should be complete enough to try to run it. Okay, so we get an error on the line. It doesn't work. You know, of course we got an error on the line. It doesn't work. What else would we get? Okay, so the error that it got. So let's take a look at that real quick. So it says warning dereferencing a void star pointer, and actually that one's just a warning. So we'll keep going. But then it'll say error call object is not a function or function pointer. All right, look at that and say, but of course it is. Well, yeah, we know that. The compiler doesn't know that. So we have to explain this a little bit more. And the fact is, it also doesn't quite know how to proceed here, simply because, where is it? Let's get back to this. It doesn't know how big of data type this FL points to. FL is a memory address, and we know it points to an address of memory addresses that are 8 bytes each. But see, you know, this I here, what if it's supposed to be like integers or something like that? You know, the compiler doesn't know yet. Okay, so we just have to add information here. And so we know that this is actually a list of function pointers, and so we should be able to cast it to something. I suggested to a number of people that we do kind of a 2-step process here. Here's how that one comes out. So we'll go ahead and declare something of a function pointer type. So we can say right here that it's a function that returns int, and I'll call it FP for function pointer, and it takes an int. And we'll start it out at this 0, that's fine. Actually, we don't even need to initialize it. And then down here, so we got to extract one item at a time from it. So let's say we want to say FP equals FL at I. Can't quite say that, FP. The reason we can't quite say that is we haven't handled the dereferencing a void star kind of issue. So let's make one of those. FList. Okay. And we'll see what happens. Okay, val undeclared. Yeah, it is. Too few arguments to function FP. Yeah, it takes the parameter. Expected semicolon before the other thing. Yeah, just right there. Assignment to incompatible pointer type. Oh, we made a mistake. Tester, I think it's in here. Sorted copy takes an int pointer and a size t. Here it's an integer and an integer. That'll be it. Okay. And then the other one, compare. I thought it was called compare. Oh, just got H. It is called combine. That would be it. Okay. Or combine. You're around here. Do some harvesting. Okay. So there we have it. Now we had a whole issue here come out later with this sorting one. Oh, we returned the wrong answer. Yeah. Isn't that interesting? I don't really care about the double free problem, but that other one, that could be a problem. Here, we'll fix it. Okay. That'll fix the double free thing. Okay, but the wrong answer. I didn't expect the wrong answer. I thought we had it right. Okay, so max index is I, so if our value that we get from our function pointer there is greater than the index. Okay. Ooh, we should solve all these errors. We shouldn't leave warnings in it. Makes an integer from a pointer without a cast. Well, that's because I put it on the wrong one. That should help. Ooh, be undeclared.
Oh, yeah.
Blend. There we go. There we go. Make clean, make nothing. Okay. So the sorted one doesn't work. We passed back, you know, an initialized memory block. But it doesn't crash it. Anyway, find best works fine. Okay, so. Okay, that's what it's called. Solution.c. Okay, so that worked. Putting all these things in these individual ones like that. Now there's a couple of implicit casts going on here that we didn't actually have to say anything about. And the compiler didn't object, so we're okay. We made flist there a void double star. Used to be a void star. And we didn't bother to cast it. That happened automatically, and the compiler was okay with that. In general, if you have two types and they're both a memory address, you can go ahead and assign one to the other without informing the compiler first, and they'll be okay with that. Same thing as with malloc. Malloc returns a void star. We didn't explicitly cast it to an int star, and the compiler is fine with that. So then we have another one right here, where flist at position I is actually giving us a void star. It's a void double star, and so we're dereferencing it once when we do this. And we're getting a void star into FP, which is another pointer type. So again, we're copying memory address type to memory address type, and that's all okay. So everything's fine. So that works. Now, there's other ways to do this. So if you look at this, you might say, well, wait a minute. So sure, maybe the optimizer will take care of it, but this is really kind of a bad way to do it because we declared an extra variable named FP. Surely we can't need that. And we declared an extra variable for that FList. We can't need that either, right? So let's eliminate these one at a time. Let's take that one out. And so we'll say F list here. Let's do one thing first. Just a throw warning. We'll just say call this a void double star up here. So if we do that, so it says warning, assignment from incompatible pointer type. That said it will work. Okay, so the reason it's throwing this warning is what we set up here is that find best is a function that takes a void double star, an integer, and a size t. But then down here, when we make this assignment, this is where the warning comes from. Find best inside this bundle is supposed to take a void single star. And so this is the wrong type of function. And so the compiler warns us about it, but everything actually works.
Yeah, I ran into that too.
Yeah. So if you don't want the warning, this has to be a void star. So up here, we could, for example, just cast it as a void double star right here. Okay, now we're going to get a really weird error. So we got a warning dereferencing a void star pointer, but we just said it's a void double star. And then later we got an error, invalid use of void expression. Okay, so the problem here is order of operations. We're doing this first. So effectively what we've got is that. So if, that shouldn't change anything. Yeah, same thing. So we're trying to dereference our void pointer and getting ourselves into trouble. And then we're taking the thing that we took out and casting it as a void double star and then assigning that to FP, which is probably giving us another issue. Yeah, well, no, maybe anyway, it's unhappy. Okay, so let's go ahead and fix the order of operations there. Okay, so we'll cast FL as a void double star, and then we'll dereference it. Okay, everything's happy. Did it work? Yeah, it worked. Okay. So that was good, but you see, you've still got this FP in here. Surely we don't have to have FP. We don't need to have FP. But we have to cast a lot of things in order to get rid of it. So let's get started. So that's what we have above there. Int val equals, we'll delete those top two lines. There's 2 lines above this in a minute. So int val equals, now we've got to call something directly out of the list. So what we have to do is correctly cast the type of that list. So FL, what we have here is a pointer to a function that returns an integer, but it's actually a list of them. And so double pointer there, and it takes an int. Okay, so that's the type. So we want to cast FL as that type. And we want to do that first, for order of operations. And then we want to call function I, get item I out of it. And then we want to call it. What are the odds I got that right? I got 1 in 10. Expected a parenthesis. Oh, yes. That's right, because the whole casting type needs to be in parentheses. That's how you do a static cast. Okay. And that works too. So I was sort of steering people a little bit away from that solution just because it's too many ampersands and parentheses and brackets on one line. And even if you get it right, nobody's going to understand how it works as they look at it. They'll just be like, okay, we will assume that that line works. And it's easy to hide bugs that way because if you're going to have a bug and you want it to take a really long time for anybody to find it, so I'm teaching you how to be a disgruntled employee who's leaving here, and then you have to put it in the most complicated line that nobody wants to really look at. But you should put a secondary bug in one of the really simple lines that nobody thinks might have an error. And have the two kind of reinforce each other. So you fix one and doesn't fix it and still looks broken. Fix the other one, same kind of thing. And nobody will do that. Look at the most complicated line and just like the simple area at the same time. Take forever to find it. Okay. So anyway, that's the cast there to do what it needs to do. This is probably, in some ways, the best solution since it doesn't have any extra variables. It's just the most convoluted. Okay, so the static cast part, I added these parentheses and didn't explain very well. So this is the parentheses for the static cast. Remember, when you do a static cast, like suppose you have this thing G and you want to cast it as an int star, you do that. Okay, F equals that, int star F. Okay, so these parentheses right there, those are the ones that I have highlighted up here. Yeah.
Someone off-topic question.
Sure.
What's the difference between malloc and calloc?
Calloc initializes the memory to something or other. So if you look at calloc here, it's got a number of members and a size. And so it actually takes two parameters here. So it allocates memory for an array of num_memb elements of size bytes each, and then returns a byte of the allocated memory. And the memory is set to 0. So with malloc, it just so happened that we were getting memory that's set to 0 anyway. So unfortunately, this is going to look exactly the same. But what we have is, which order is this going again? I forgot. We have the size, or the number of members first. Okay, so the number of members we have there is len, and the size of each member is size of n. Okay, and so now we want calloc instead. Okay. So you can see it didn't change anything. So could we make it change something? Sure, we can do that. Okay, let's switch it back to malloc for a minute here. So if you want to switch back and forth, change the letter, change the comma to a times, and that'll convert. Okay, here's what we're going to do. We'll say malloc, and we'll say len times size of int, and we want this to come into some sort of array. And okay, then we'll go ahead and say array at position 5 equals 100, free array. Okay, so what I'm hoping there is that when we run malloc again, we're going to get a spot on the heap that happens to be the spot we just freed, in which case we'll still see that 100 there. That's what I'm hoping for. Of course, this behavior is not guaranteed, since we're dealing with uninitialized. Well, you can see how it's kind of, okay, hey, it actually happened. We got 100 there. Okay, so let's change to using calloc. Look at that, zeroes it out. So that's the point of calloc. Okay, any other questions on this? This C in memory is a totally valid topic. Okay, so that's casting and ways to solve this project. I'm not sure anybody used exactly that one, but I'll find out whenever I get to grading these things. Okay, let's see, system function. I wanted to mention system because I didn't talk about system before. Go back under software. Let's go back off of my software. Okay, I changed my mind. So I'm going to go ahead and mount the examples directory here. Okay, so last time we did, we used fork and exec to start the browser. Start browser.c. And we have the parent here staying there, and we have the child call exec_cv, and go ahead and start the browser. Now, looking at this, you can see that this is probably kind of a common thing to do in a C program. You want to start some other program, and you want it to keep running. So the fact is, there is a function that makes this kind of easy. And it's called system, execute a shell command. This actually does wait for you to finish, so it handles fork. You can see up here it mentions a system library function uses fork to create a child process that executes the shell command specified in the command argument right up there. And so it returns after the command has been completed. So it'll actually wait for the child to terminate and in return control back into your process. So it handles kind of a complete fork exec cycle all for you without you having to do much of anything to run it. So let's try it. It's in stdlib. Okay. Okay. So return 0. Okay. So I'll go ahead and say printf to run the web browser. Okay. And we'll say system. Where is it at? Actually, I don't think we need to know. I think it's fine if we just say Google Chrome. And then we can give it a website to open up. Does that actually work? I don't know. Yeah, it works. Okay. So that's what we want to run. Okay. Now, one note about Chrome. We can circumvent this. Okay. So I'll go ahead and build it. Give us a warning because we didn't remember to actually put stdio for printout. Oh, don't make that one. Okay. Okay, so 8IO. So there it goes. Now, here's the thing that I was mentioning it's going to do. It says done running the web browser. Notice the web browser itself printed out something about the accessibility bus, which it failed to connect to, and it also said it created a new window in existing browser session, and then our Google Chrome command actually terminated because it talked to the existing process and set that window up. If we close the web browser like that, all gone. That's my window list. I just got one terminal. And we go ahead and run this. We got the web browser. And then we switch back to the terminal. You can see that we're actually stuck until over here we decide to, I'll do them separately. So it's waiting there. Close this, and it's done down there. Okay. So anyway, that's use of the system command, and one way to go on that. Oh, it's not recently closed? I would have thought it'd be like top of my history. Okay. There we go. Okay, note on process adoption. So we talked about process adoption, and something has to wait on the child process until it gets waited on. It stays as a zombie. And so I wanted to show you a little bit of the mechanism inside the kernel for that with the find and reaper function. Okay, these are the Linux source 4.9. Okay, it's in kernel exit.c. Okay, and look at that. My cursor's in exactly the right spot because I was looking at this morning because I wanted to explain it without mumbling too much. Okay, when a process dies, when we die, we reparent all our children and try to, first of all, give them to another thread in our thread group. Processes are organized with these thread groups, and so keeping it in the group can help, if such a member exists. Otherwise, give it to the first ancestor process, which is a child subreader for its children. It's self-identified as that. And then finally, 3, give it to the init process if we have to. So I actually have a loop here that runs through its for loop and tries to find a process using this set of logic. Anyway, it gets convoluted at this point if you try and read through the code, which is why they put the comment up here in order to explain exactly what it does. The file here, exit.c, is full of the functions in order to make processes get adopted by other ones, like this forget initial or forget original process function. So each of these tasks are represented by this struct tasks struct. And you can see this is passed around as a pointer for it. Now, when you pass around a struct task struct like that, let's get back up to this one. You can take the memory address of this struct and then compare it to things. So here we have this for loop, and we start out reaper equal to father. Reaper here is a struct task struct pointer right there. So each of these are pointers to a struct task struct. Remember that you have to use this second asterisk. If we were missing this, then thread is a struct task struct pointer, and reaper is an actual struct task struct, not a pointer to one. It's kind of one of these gotchas on these declarations. You actually have to say that the star is a property of the individual variable being declared, not of the type. I try to remember not to do that because if you put the star there, like this still works like this. But if you put the star here, it makes it look like you definitely don't need it over here, like it's part of the type. Anyway, okay. We got 2 memory addresses there, and we can actually compare them. So this for loop here is actually assigning one memory address to another, and doing this, and later here we're checking to see if the memory address is the same as another one. That's one way to check and see if 2 objects are exactly the same object. It doesn't do a deep comparison, it checks to see if they're the same memory address, and if they're stored in the same spot, then they must be the same object. Yeah. I just realized we hadn't done that in any of our little examples. Okay, other than that, we just go through the little algorithm there to try and do what it says up here in the comments. Okay, and the whole library of functions to do that is in here. Okay, so there's the note there. So, continuing with processes. We'll talk more about struct task structs a little later. We're not going to, we already did that though. That doesn't need to be there. So we'll skip that part when we get there. Okay, so let's talk about signals. Okay, now your textbook doesn't talk a whole lot about signal handling. So you type in man 7 signal. This is kind of the textbook for the signals part. Now the manual section 7 up there is quite different than section 2. So if you look at if you just say man signal and forget to put in the 7, you're going to get an entry in section 2 that describes the signal function in great detail. So it's good to know what the signal function does, but that's one random little detailed piece of knowledge there. Man 7 signal will give you the overview of how signals work on POSIX compliant operating systems, which is the what we'll cover today. Okay, so Linux supports both POSIX reliable signals, hereafter referred to as standard signals, and POSIX real-time signals. So there's mechanisms here to send a signal and catch signals and that kind of thing. There's disposition for a signal, and so disposition is what happens when the signal is received. And so a lot of them have a default action. So for example, the sig term, default action is to terminate the process. So this is what happens with a signal if you don't handle it. So let's make some kind of program. Let's make some sort of program. Print messages. Let's see. Okay. Find the page. Delete both of those. Good boy, man. Okay, so let's say 4. This is an infinite loop, by the way. So you might say, well, infinite loop. So I need this. While 1 or 2. Hey, that would work fine too, actually. Anything that's non-zero is true. That's a good infinite loop. But this is also an infinite loop. And sometimes that status, the 4 colon is favored in some coding circles, coding styles, but it's not always, because you can make one either way. And so I'm going to do it like this, just to leave the other way in here. You got to be familiar with all these different ways. Okay, so that's an infinite loop, and we're going to say printf hi, the hi sayer. And then we'll sleep for a second. Then we'll do it again. Okay. Ooh, that wasn't where sleep was. I thought it was in time.h. And it's not the section, not that one. Okay, 3. 3, unitstd.h. Okay. We can change that. Okay, so there we go. Work? Yeah, works great. Okay. Now, we will eventually get tired of this. It might take us a long time. It's pretty exciting. But I think I'm tired of it. So I'll hit Control-C, and it will stop. So what we did is we handed it a signal. And default action on the signal was to terminate. Okay. There we go. So default action, sig term, is to terminate the process. Cool. Okay, so the process can change the disposition of a signal using sig action or signal. The latter is less portable when establishing a signal handler. See the signal and page 2, when I pulled up earlier for details. Using these system calls, the process can elect one of the following behaviors to occur on delivery of the signal. Perform the default action, so generally, ignore the signal, sure, or catch the signal with a signal handler, which is a programmer-defined function that is automatically invoked when the signal is delivered. Yeah, let's do that. Okay. A lot of ways to do that. Okay, so you mentioned that you can use either sig action or signal. If you look at signal, NCC signal handling, you give it a sig handler, and that has to be a sig handler type. And so sig handler type is a function that returns void and takes an integer. There's an interesting note up here in the description. The behavior of signal varies across Unix versions and has also varied historically across different versions of Linux. Avoid its use. Use sig action instead. Yeah, sure, we can do that. Okay. So, sig action has no such note, which is good. Good first step here. And sig action is a little bit more complicated to call. That's the unfortunate thing about it. So sig action, we give it a signal number. That's the number we intend to install a signal handler for. Then we give it a construct sig action by reference, so a pointer to it. That's the action structure. So the sig action to structure, I love this note, is defined as something like this thing down here. On some architectures, a union is involved. Unit assigned to both SA handler and SA sig action. So by something like, it means that there could be a union involved in this in some ways. And in fact, as there probably is on this architecture. The reason for a union, so you don't normally use SA handler and SA sig action at the same time. And so if you're not using both of them at the same time, then we really don't need to allocate 8 bytes for each of them. They can use the same 8 bytes. And so a union is a method to do that. I haven't shown you a union, but that's what a union does. It's a lot like a structure where you can only assign one member. So you can nest a union inside of here and save a little space. And so on most architectures, that's how it's done. So that's why they say it's defined as something like this. Okay. We can make one of those, one of these sig actions. Okay. And then it's got the struct sig action. No, it's not a const one. That's because it's going to change it. Struct sig action star old action. And so it can actually give us the previous signal handler. So if we wanted to temporarily switch signal handlers for some reason for a while, we could do that, and then we could put the old one back later. We don't really care to do that. If you don't care to do that, you can pass a 0 right here. It says that someone. Okay. So that's what we need to do. We need to declare a struct sig action, and we're going to make this thing based on it. So print, what do I call it? Print messages. Okay. So I'm going to actually pull in that man page below. We'll split the window here this way, and so there we go. Okay. So we have to include signal age. Okay. Then we need our call sig action up here. And so we need to say what signal number we want to handle. So we'll have to look that up. We'll do that in a minute. And then we got this action. Okay. And we got to pass in by the address of it and the 0. Okay. So for that, we have to make a struct sig action. And so that works like this. Struct sig action. Action. So that's the name of our struct sig action. And then we can set things in it. We can say action dot SA handler. And so that's going to be our handler up here. So we'll go ahead and say, so you can see down here for the profile, it returns void. And we can call it whatever we like. We'll call it our handler. Okay, handler. And then you can see it takes an integer right there. And that's the signal we handled. And we'll go ahead and print something out. Okay. And so there's function. So that's what SA handler is. Okay. And then we've got a mask here. I don't think we actually need to put anything on the mask, and we don't need anything on the restorer. We probably don't need anything on the flags. So you can modify the behavior of the signal. And so it's got a few things we can do here. I don't think we really care about any of them. We should probably set it to 0, I suppose. Okay. Might not actually need to do that. Okay, so that should install it. Oh, but the signal number. I haven't looked at that yet. Okay, so I'm going to close that man page and go back to man set on signal. And actually, I'll temporarily take this out too so you have my face. Okay, so I mentioned some examples on one. So, signals. We have a sig quit. That's value 3. And that's a quit from keyboard. We've also got a sig int, value 2, term. That's the default action is terminate. Interrupt from keyboard, sig int. That's the one we want. Now, sig int is number 2. So, on this thing over here, we could write, that's not usually favored, because not everybody has a signal table memorized in their head. So if you say sig int, that's actually defined, and it's marked with red here. That's defined if you're inside signal.h, and people are much more likely to know what sig int is than what we mean by 2. Okay, let's go ahead and make that again. Okay. Oh, incompatible types. Let's take that out for a moment. See what works. Okay. There we go. There we go. Control C. Control C. Control C a bunch of times. So we made something that ignores the usual mechanism there of Control C. Now it's not, it's there daring us to kill it, and the fact is we probably can't. What about Control Z? Well, we stopped it. We haven't killed it. If we say PS, we can see the processes we have running. One of them is A.out. So if we say kill all A.out, yes.
Still there.
We bring it back. Oh, no, it was terminated. Yeah. All gone. Okay, so yeah, there's other ways to get around it. But what's the kill signal? Sig kill, 9. I'm not sure we can actually stop a 9. We can certainly stop. Now we stopped the process there with Control Z. It's got a stop process there. We got a stop type to terminal sig TSTP.
Sig stop.
Yeah. Okay. Well. What was it before? It was like spelled weird. Sig TSTP. Okay. Okay, we'll build this again. ECC on. Okay. Control Z. Control C. We're doing better. Okay. Now,
We're
it's not quite
a
vulnerable
process.
Got it. From a different terminal. We didn't have much we could do with that terminal, but so that kind of worked.
This almost sounds like the basis of a really annoying virus.
Yeah, kind of. Yeah. So what was that one? So we got a signal from there, from kill, and it killed it. You've got sig kill is 9, but like I said, I don't know if we're allowed to do that one. How about sig term? Maybe that's what we got. Okay.
Because it does say terminated.
Yeah, it does. Okay. Okay. Here's our second terminal. So yeah, the program can become difficult to kill. Because now if we go up here, we do Control C or Control Z or kill all. Yeah, it still is. Oh, here's an interesting idea. X kill. Well, X kill the terminal.
You murder the whole terminal.
Okay, the terminal is gone. Here's a new terminal.
But that process is still running. Yes.
I think we already got it. I think I did it. Yeah. So there's still ways to get around it. But here's another one. You see examples. Okay. I keep talking about that 9 down there. So we got it running down there. Kill all. A.out. Kill 2 L's. Okay. It can't kill us. But what if we say -9? That kills it. Okay. Now, if we looked at the man page on that one, man 7 signal, you'd see we actually have it. It's signal 9 right there. Sig kill. Search for sig kill in here. Signal 9. Now it mentions down here the signals sig kill and sig stop, which I guess we tried to catch, cannot be caught, blocked, or ignored. So you might say, well, sure, why not try it? What's the harm in trying it? Sure, why not? Okay. So sig action, sig kill action. Okay. so if we make the terminal down here, and we say kill all -9, A.out, snap to
Still
nothing.
kills it.
It's not actually delivered to the program. The operating system takes single line and kills the program without consulting it first.
So what you're saying is it's assassinating the program.
Yeah, well, yeah, it's removing it from the outside. It's not asking it for permission first. I mean, the other one's a very polite, will you die now?
And then your condition gets checked. And
Right. So you can still get rid of them with -9. And so if you ever are on a Linux system and there's some program and you can't seem to kill it by just using regular kill, use -9, and that'll take care of it. Send a signal line. It's your system. You can kill the process. Okay. So that's what signal. One thing signals can be used for. We made a program hard to kill. Yeah.
So could we use -9 to kill things that we really shouldn't
Yes.
in Linux?
Yeah, you can.
Absolutely.
Yes. Being administrator and having -9 at your disposal can be a pretty deadly combination.
You could do some really stupid things.
Yeah.
Trust me, that was something we did in my Linux class in the IT side is
Right.
break things to break things.
Yeah. Okay. So with signals, so I have trouble not singing the "Do You Want to Build a Zombie" because there was a recent popular animated kids movie that has a title song about building snowmen that my kids listen to on a regular basis. The fact is, I can actually walk up to a piano and play it with my eyes closed. Just because I've heard it. So but yeah, let's go ahead and make one using signals. Okay. Signal zombie. Okay, so okay, so we'll go ahead and include fork here. Oops. Okay, actually, we'll go ahead and make a copy of something. We'll start with something. Okay, we had this thing, and I think it was called fork exec. Forkexec.c. Okay, signal zombie.c. And so this thing made had a child here that took a long time. Let's go ahead and say the child takes too long, 50. We'll go for 48 here. And so we'll do this, and then we'll say, tired of waiting for the child. Okay, and we'll wait for the child eventually, but we won't do it later. And so when we're tired of waiting for the child, we want to send it a signal. Okay, so question there is, can you send a signal from a program? And the answer is yes. If you put man kill, you'll get something from section 1, and this is a user command that you can type here. So if you go for section 2, on the other hand, then you can find the kill that we're looking for. Send a signal to a process. It definitely has an idea about what signal you might want to send. Of course, you can send any signal you want with it. You can actually do that with the regular kill command too. You notice with kill all you can too. I said -9, like send signal 9, and it was happy to send signal 9. We could have said, -3 or something and sent signal 3. That would have been fine. Okay, so kill can be used to send any signal. So you give it a process ID and a signal that you want to send it. Okay, so over here, if we say kill, and so the process ID we want. So result was the process ID that came back from fork. Right up here, that's the process ID of the child. Okay, and then we need the signal that we want to send. Okay. So there's the table. I think I want to send like a sig int or something. Sig int, interrupt from keyboard. Sure, why not? Okay. Sig int. Okay. And then we'll calculate the Fibonacci number, or the 49 Fibonacci number, and we'll finally wait on the poor child. Okay. So there we go. Okay, so I want to put this down here, and I can write GSAXU grep a.out, and we can see it running. The child is running, the parent is running. They're both running together. I guess that's good. The child's process ID is apparently 4014. Our program printed that out. You can actually see that there. Okay, so now the child is a zombie because they've been killed because we got tired of waiting for the child, and the parent is still busy doing this thing, and so we're left with the defunct zombie process for a while. So if you wanted to spawn zombies for some reason, you can totally do that. So what do I call that thing? I don't make zombie. Signal of zombie. Okay. Making a zombie by a signal. Okay. So we could totally actually encapsulate that if we wanted to into a zombie making function. We could call this thing something like void min-k zombie. Okay. Giving me the parameters. And so what we want to do here is first of all fork. Okay. Now if we're the child, so say if not result, then what we want to do is just like run forever. And so we'll say fib of say 60. That should keep it busy. Okay. Otherwise, and then we probably want to exit actually. Just on an off chance it finishes. Okay, so otherwise, we want to make them a zombie. Oh yes, we want to kill them actually. I need to say this PADT. So again, it works fine. And we'll leave them killed, but we will be careful not to wait on them. Okay, so then down here, for our zombie making program, we can go ahead and do that. We can say something before and do that. Okay, print up making 10 zombies. What 10? 100. Okay. Okay, and so what we want to do is MK zombie. Okay, good. Okay, I shouldn't finish for a long time. There we go. Okay, so we got a zombie making program. Implicit declaration exit. We don't actually need exit there, but it's an stdlib apparently. Okay, so do we have 100 zombies? Yeah, we do. There we go. Look at that. Okay, so the program here does that. And it says it's keeping the CPU warm. Is it doing that? So we can see it's running, but that doesn't necessarily mean it is.
Yeah, the zombies really are there.
Sensors. So, you know, we're kind of doing it. Like, it looks like one of these cores is up at 42 centigrade, and actually that's the temperature of the adapter sensor, wherever it is. Now, some of the cores are still pretty cold, like 29 or 35 or whatever. If we keep running it for a while, you start to see an improvement in the other cores. You can see we've just got one that's at 29 there. If we go ahead and run this again, well, you still got a couple of them down in the 20s. I don't know if it's really doing the job. But anyway, there we go. Would you feel warm if you were 29 degrees centigrade? No. Okay, so that one can go away, and that can go away. Cool. Okay, so the what is a kernel track? Let's actually get to that in a minute. We'll run down there, and we'll come back and get that one in a moment. Okay. Let's talk about time slices real quick and scheduling policy, and it will have to be quicker than I really wanted. First thing about scheduler history. So the early scheduler in Linux tended to scale badly. And so scaling badly just means having trouble dealing with a large workload in this case. So we got, we looked at PSAXU before and how there's like 200 processes running on a computer. And so the scheduler has to have some efficient way to go through all the processes and figure out what ought to happen, especially if somebody comes along and adds 100 defunct zombie processes to the process table. So there's got to be some scheduling that went. So shortly after the badly scaling scheduler, there was a little bit of an overreaction, and I think Linus wrote an order 1 scheduler. Doesn't scale any better than that. And better than that would mean it gets to run faster when there's more data to deal with. You know, that's pretty rare. So it was pretty fast. And order 1 scheduler worked pretty well, but it had a little bit of trouble with latency-sensitive processes. And a latency-sensitive process is mostly an interactive process. If you got something that the user clicks on, they sort of expect it to jump at their command, right? You know, you don't expect it to get around to it later. If you talk to somebody and you're like, "Hi, how are you doing?" And they're like, "I've been pretty good." You know, it's like super disconcerting and weird, right? Some people don't like their computer to do that, but they expect the computer to react within milliseconds when they click on something. You know, if we click on this thing up there, we expect it to be highlighted right then. And so in order to do that, the scheduler has to allocate a time slice to the web browser so the web browser can go do something, you know, right away. And the order 1 tended to deal stuff out in a pretty fair way, and it didn't spend a lot of time thinking about who ought to run. So it's pretty good for a server process or something like that, but it had some trouble. So eventually that was replaced by the completely fair scheduler. And the completely fair scheduler has a really funny name because when people look at that, they're like, wait a minute. I think Linus has been too deep in these processes. I mean, we got to be fair to the processes. Do we have to be worried about their feelings now too? Because, you know, there's computer programs, right? Anyway, but such is the name. Anyway, it does more of a balance that is intended to be kind of a fair compromise between interaction, like quick interaction and responsiveness, versus handling long time loads. You see, if something's going to run for a long time, it's nice to allocate a large time slice and not keep interrupting it. You know, if you're working on a project and you expect that the project is going to take 10 hours, and somebody decides that they're going to interrupt you every 46 seconds, you're going to struggle to progress, right? And so that's what happens with short time slices on the computer. There's a certain amount of overhead involved in setting up a process. Think about back to CS250, I probably remember registers, right? Little areas you keep stuff on the CPU. And so if you're busy writing an assembly program and all the registers change in the middle of it, is that good for your program? Nah, you get undefined results, right? So one of the things that has to be done to switch processes is all the contents of the registers have to be removed and saved. And then for the process we're switching to, the contents have to be retrieved from memory and put back into the registers so that the other one's ready to get going again. Basically, it's got to have the state it was in restored. Everything, including CPU flags. So this takes a certain amount of extra time and overhead. So the completely fair scheduler allocates a variable amount of time depending on how the system seems to be acting at the moment and what's being used on it and that sort of thing. Processes that haven't had any attention for a while build up a higher priority. And the justification here is, suppose you're doing two things. In the background, you're ripping a Blu-ray and encoding it to remove the DRM because it's yours anyway and you want to keep it on your hard drive. But while you're doing that, you're also surfing the internet and clicking on links. So the web browser is going to be consuming far less CPU time than the Blu-ray encoding process, which has probably spawned off enough processes or threads, one or the other, to use up your entire CPU. So it ends up with a really bad priority level, and your web browser hasn't used much of anything, so it's got high priority. And so when a web browser actually wants a resource, it gets it. And when an encoder wants a resource, it gets it if nobody else is using it. So that's the way that works. Now, it does mean that on a completely fair schedule, and I haven't tested this to be absolutely sure, if you start your DVD encoder and you start a video game, you probably don't want to do that combination. Like, it would be better if you do the encoding at different time. And everybody's nodding like, what idiot starts a Blu-ray encoding and then goes and plays video games on the same computer? And yeah, I mean, you're right. But it might be cool if there was some way to handle it. Actually, there is. You can set the niceness manually. Processes have a priority level associated with them, but it's actually stated in an inverse way. Processes that are more nice are quicker to let other processes go first. The maximum niceness level is typically 20. So what you want to do is set the niceness of your DVD encoding system to 20, and then go play your video game. You might even want to manually set your video game to be as mean as you can. Niceness 0. then it'll do what you want. Okay, it'll still might not be absolutely perfect because if your video game doesn't need something, it's still going to get unloaded, and you'll have a chance then. Okay, I feel like I should fire up a video game and Blu-ray
I
encoder.
was gonna say, but not too long ago, I've done that very thing. Burn and rip a disc while I'm still playing a game and never had much issue, but of course, most of us are running on, hyper-threaded quad cores and.
Right, and it helps a lot because when the time slice is allocated, and the process runs until it runs out of time, and then it's interrupted regardless, and the operating system can schedule it again later. But if you got multi-cores, then you got more time slices ending per second, and so you got a lot better chance for the game to get some attention. Yeah, the multi-core and hyper-threading really made the interactive nature of systems a lot better.
Oh, yeah.
And it seems weird in a way, but even browsing the internet, it's nice to have 2 cores, at least. Because then you get a tab that's stuck running some ad the whole time, consuming 100% CPU. Your system stays responsive.
Most of us old schoolers are used to that concept of, all right, you're doing something with your computer, that's all you do. You leave it alone and let it complete its task.
Right. Right, you kind of think about load, Or you might say, oh, well, here's my plan. I know my game's multi-threaded. I'll tell my Blu-ray encoder it has to use, less threads than I have processors. Most of them will let you say that. Okay, so that's the time slices. So these time slices are given to a process, and it gets that long, and then it gets interrupted. And it's not like a parking meter. Parking meter, when it goes off, you're safe until the police notice. I think in Bellingham, Washington, they have it set up to automatically notify them if it detects a car in a parking spot and the meter's expired. I say that because I've watched the parking lot before, and when a meter expires, the ticket officer drives to that car that it expired on. Like, he doesn't go check them, he just drives to that one. So don't let it expire if you're in Bellingham, Washington, in the downtown area. But anyway, in general, it's once it expires, you're on borrowed time, but you're not immediately in trouble in general. With a time slice, when it ends, you're automatically interrupted. And so the operating system will stop the process from running and decide what to do next with that core. There we go. Okay, so scheduling policy. Input output bound. IO bound is a funny one. So you can have IO bound processes pretty easy. In fact, our Blu-ray encoder, if we were instead of encoding it some other way, we were just like ripping the disk and putting it on our hard drive, we would quickly become IO bound. We're waiting for the optical drive to remove data. It used to be that the processor had to broker these kinds of transactions, and so it would actually keep your CPU kind of busy, taking information off the disk and squirreling it away on the hard drives. Later, there was a system added called direct memory access, or DMA. People who tried to build a computer in the 90s are probably quite familiar with DMA. Anyway, so DMA, direct memory access, lets the processor tell a drive to start stashing all the information in a particular region of memory and just kind of, get going and, I'll talk to you later. And so then the processor doesn't have to be interrupted all the time. That helps a lot with an IO-bound process. But sometimes you end up with an IO-bound process where that's just not possible. If you've got some like minor action that's supposed to happen on all the incoming data from the Blu-ray drive, then you're going to have to funnel all this through the processor, and it's going to need to queue up for a while, and then off you go. So a lot of the functions for IO-bound actually cause interruption. So take read, for example, read from a file descriptor. Read attempts to read up to count bytes from the file descriptor FD into the buffer starting at buff. Now, since hard drives are slow, it might take a while before there's anything there. When you call read, it probably has a note on this somewhere. I don't know where the note is. But anyway, when you call read, if you're in the middle of a time slice, you actually kind of give up the rest of your time slice because you're going to be waiting for some disk operation to complete. There's actually quite a few functions, what system calls, in the library here that will cause the rest of your time slice to be forfeited. Here's another one we called today. Maybe this is section 3. this will forfeit the rest of your time slice. When you call sleep, you ask the operating system to wake up your process again in however many seconds you set. Well, until that time, the process is put into a sleep state where it's not actively running and it's not eligible to run. It becomes eligible to run again after the sleep is expired. And once it becomes eligible to run, the operating system can schedule it and give it a time slice. Now, you shouldn't use this function for precise timing. The reason is, once the timer expires, instead of immediately starting at, say you give it 2 seconds, instead of immediately starting at 2.00000 seconds, at 2.0000 seconds, it becomes eligible to run. And then it doesn't actually run until the operating system decides to allocate it a time slice. If all the process cores are currently working on something, then it might be a little while, depending on how long the time slices are and what's been allocated. And so this is why the operating system will try to allocate it, some short time slices so that some cores are interrupted soon, so that they can be used to schedule other things that might have just become eligible to run.
And it would also be dependent on how friendly those other processes are.
Right, exactly.
They might have a high priority level, and you're like, no.
Yep, that's right. If niceness is set to 20, you get CPU time when nobody else needs it. Okay, so there's been a lot of money spent on the Lockheed Martin F-35-2, which was called the Joint Strike Fighter, for quite a long time. The F-35 uses the operating system on the, remember, airplanes have operating systems these days. So the operating system that runs in the F-35 is Integrity DO-178B. And so we go look at this operating system, the Integrity family of operating systems, produced by Green Hill Software. So if you really like operating system level coding, you might see if they have a job for you at the end of the degree. Anyway, so it's a POSIX certified. Hey, look at that. If you write a program for Linux, you can compile it and run it on Integrity. POSIX certified, intended for use in embedded systems. Now, the Integrity 178B is version that's used in several military jets, such as the B-2, F-16, F-22, and F-35, and the commercial aircraft Airbus A380.
Yeah, I flew on one of those.
Yeah, so if I was Airbus, I would totally put that on promotional literature. Uses the same operating system as the F-35. Why not? Anyway, so its kernel design guarantees bounded computing times by eliminating features such as dynamic memory allocation.
No DMA.
Yeah. It's got this assurance rating and whatnot. So, and it supports multiple architectures: Power, AMD, ARM, and MIPS. That's not what I wanted. I don't know where that came from. Okay. That's what they do. Okay. So what they're doing here is making it a real-time operating system where you got a guarantee about things. So if you imagine you're flying along in your F-35 and somebody launches a missile at your aircraft, you might like it if there was a guaranteed time when the computer would actually respond. With Linux, there would not be a guaranteed time the computer would respond. If it was busy encoding a Blu-ray because you decided to do that on an airplane's computer while you were flying for some reason, then it might take a while before it finished a time slice and started thinking about what to do here.
Hey, sometimes while you're flying around, you just really want to watch Top Gun.
Right. And if you're flying along playing World of Warcraft. So anyway, that's it's behind real-time operating systems and time guarantees. Okay, source model, closed source classified. That's like the most closed source option.
Yeah, I don't think you can get any more buttoned up than that.
Okay, so anyway, there's I/O bound and latency. How long does it take to get a turn? Sort of depends, but that's something the scheduling policy has to work on. Okay, fraction of the CPU used affects preemption. Yeah, they have this kind of characteristic in CPU scheduling where if somebody's been there for a long time, then they get ordered out. I have kids, and one thing that kids enjoy, if you ever have them, is bouncy castles. Where it's just giant inflatable structure, and you put in all the kids, and you jump around until one of them bashes their head into another one's teeth, and then you collect all the teeth, and it's great fun. Anyway, so there's a lot of stuff like that. I mean, I have a trampoline in my yard, same concept. Okay, but usually they're scheduled with a time slice of time when they're allowed to turn in there, and then if they've been in there for a long time, then they're sent back out. And so if you had, for example, 5 kids in the bouncy castle, and you have kid number 6 and they're late to the party, and you want to give them a turn, you'll usually preempt the one that's been in the bouncy castle for longest. Why that one? In some cases, certain other considerations might override it. For example, if one of the 5 is actually 2 and they've been sitting in the corner crying about not being able to get out for a minute, then you might take them on instead. Or if one of them has been attempting to puncture the bounce house castle using smuggled in plastic cutlery, you might all preempt that one. I would. The thing's probably rented. So anyway, that's the concept totally pervades a lot of the CPU scheduling. Okay, input-output interrupts the processor. Okay, it can. I'm going to talk about mice for a minute. So this is a mouse. These are newfangled gadgets intended to deal with graphical operating systems. We haven't always had them. If you're ever found without your mouse for a moment, you might find it disconcerting at first, but the system is actually pretty operable without a mouse. Now, I was going to look for a mouse that's, I was going to unplug that one from the computer, but let's go find a different one. They say when you're giving a lecture, you should move around the room occasionally because it adds interest. But they haven't mentioned unlocking doors. Unlocking doors provides further interest because one never knows what kind of prop you might have hidden behind the door. I could pull out an inflatable dinosaur. With that said, I'm going to know what I'm going for. It's going to be a mouse that I can find out. Okay, perfect. This is exactly what I wanted. Okay, so this one has a rectangular plug. It's a USB interface. Stands for Universal Serial Bus. Probably all seen one of these. Plug it in the computer. If you have kids, you probably watched one plugged into their nose. So it works. But what they should have had to plug into the nose was something round. This is a PS2 plug on this older keyboard. And so the PS2 bus also plugs into computers. And if you look at the back of these computers here, they actually support PS2. Which you might seem odd to you, because if you look at, say, a thoroughly modern Dell from 10 years ago, it probably doesn't have a PS2 port, oddly enough. Now, we have a broken motherboard in here, and that's what I'm looking for now. Hope you can all hear me out there, okay? Here, got it. This one had an accident taking out a video card. Somebody took out the video card, the video card from one of the PCI Express slots, but they didn't actually undo the little clip that holds it in the slot first. And so they actually managed to take the slot off too.
Yeah, I heard about that.
Yeah, somebody has definitely been eating their Wheaties. Anyway, right there, see this funny dual colored round port? That is a PS2 port. So that you can plug in this old keyboard into this fairly new motherboard. They're not that new anymore. They're going to adapt to that. These things are 2 years old now. They're searching for grants any day now. Okay. In fact, I'd love to find a grant to replace them. Somebody put them down to 240 and we have 2 good labs. So that's the PS2 port. So let's say, why in the world does this new motherboard support this obsolete PS2 standard that hasn't been the main way that keyboards plug in for 15 years?
For people like you.
Well, yeah, my keyboard's older than 15 years. It's actually about, I think that one's about 23 or 24 years old. But that's not why. You can use a USB adapter for the keyboard and plug it in. I've run them on USB adapters before. Here's what it is. So on the USB, it's a pulled bus. And so this is part of why you can have so many USB devices. Now, if you look at a desktop computer, you can plug in like 10 of them. And if you plug in a USB hub, you can plug in like 10 more. And it's because it pulls. So for each device on the bus, it queries to see if the device has anything to report with a certain frequency. Now the PS2 bus, on the other hand, doesn't do that. PS2, when I push a key on this keyboard, it interrupts whatever the CPU is doing to deal with my keystroke right then. No waiting for any polling or any of that kind of stuff. It's interrupted immediately. Gamers actually say that they like that because they don't have to wait for the polling event to happen before their input reaches the system. And so a lot of gamers will run a PS2, usually a PS2 keyboard and a USB mouse. But you can run the other way if you want to, run a PS2 mouse and USB keyboard. The problem is you're going to struggle to find a PS2 mouse that has like anything later than the trackball era. You know?
Yeah.
You need to clean out the dog hair with your pencil eraser pretty soon with that kind of hardware. So usually they have USB mouse, PS2 keyboard, in some cases. Not all gamers have a USB keyboard. I'm sure you can find one in this, or a PS2 keyboard. I'm sure you can find a gamer in this room that has a USB keyboard and has at some point won a game.
Like most of them probably.
Yeah. Anyway, so that's the bus and the polling and input-output. So remember that in the way these things work. The USB controller on the motherboard will periodically interrupt the CPU with the results of the poll if there was anything to report. So the USB controller polls all the USB devices. If one of them had something to say, then after it's done with this polling cycle, it interrupts the CPU and delivers the message. So there's a little more going between. Okay. We'll talk a little bit more about this stuff later. Oh, I want to show you one more thing. This is a new plan. We're going to trial this and see how it works. So these are practice problems right here in order to practice the stuff that we talked about today. You make a program that uses a system to open a web page with the web browser. We did that when given a SIG-IN. So you give it a Control-C and it opens up a web page. Or you can modify forkexec.c to handle SIG-child. There's a SIG-child, and you get it when your child process dies. And so you can use that to wait on the zombie and not actually make a zombie process. So there's a couple of practice problems if you want to practice. These are not graded or anything. You don't have to turn these in. I guess you don't have to do them because I'm not even going to check. But if you feel like practicing, there you go. I sort of figure that people make up practice problems like that, but I'll try and include a couple at the end of each of the notes. We'll see if it works this time. So then we'll see at midterm if you guys solidly defeat the fall 17 class. No, that's my goal. Every class should defeat the previous one, right? Yeah. Eventually I have to make the test harder in order to. Okay, we'll see you all next time. Sorry, I went a minute over.